So there are some laws associated with logs, and these actually relate very much directly to the index laws. And I can prove all these laws, and I might go through and prove one of them later on. But the proofs aren't important. You just need to know the log laws. And I believe, and Brad or Harvey could confirm this for me on that math methods formula sheet, I believe the log laws are all on there somewhere. So you don't even have to memorise them. Yep. Yeah, cool. So there's 5. It's like the index laws again. No, it's an arbitrary order of laws. So I'm going to give you the 5 laws. I've actually just combined 2 of them into one at the top there, you can see already. So I'm going to give them to you in my order. Could be different in the textbook, could be different in a different textbook, could be different if you're talking to a tutor, could be different if you're talking to a year 12 student, I don't know. So the order is arbitrary. We start with the simple ones, which I think is where it's different with the textbook, because I think the textbook does those ones last for some reason. But the simple ones are this: log base a of 1 is equal to 0, and log base a of a is equal to 1. They're just standard ones, and hopefully they make sense to you. A to the power of what equals 1? Well, we know that a to the power of 0 equals 1. That's one of our index laws. Anything to the power of 0 equals 1. So log base a of 1 is always 0. And a to the power of what equals a? Well, a to the power of 1 equals a. So 3 to the power of what equals 3? It has to be 3 to the power of 1. So they're just your standard laws from your 2 of your standard exponential laws. And they may come up, and they often do, in bigger problems where they're hidden in the problem and you've got to realise you can evaluate those out. So log law number 2 is a bit more important. This is directly related to this law. A to the power of m times a to the power of n is equal to a to the power of m plus n. And I believe it's proven in the textbooks. You can have a look at that if you want. When you multiply 2 indexes with the same base, you add the powers. With logs, if you add 2 logs with the same base, you multiply the bits inside the log. So log base a of m plus log base a of n equals log base a of mn. And it's on your formula sheet, so you don't have to memorise it. It's on your formula sheet. Get used to referring to that formula sheet. So an example of that, which is an interesting example, I've chosen it very deliberately. Example 3 doesn't take too long to do, but it works out really nicely. So if I was evaluating log base 6 of 12 plus log base 6 of 3, if you want to do this in your calculator, log base 6 of 12 is an irrational number. Log base 6 of 3 is also an irrational number, but when I evaluate them, I get log base 6 of 12 times 3, which equals log base 6 of 36, and 6 to the power of what equals 36? 2. So log base 6 of 36 is 2. And that just comes from that second log law up there. If you're adding 2 logs with the same base, then you multiply the bits inside the logs. So that's a pretty easy log law. The third one, which comes directly from this exponential, a to the power of m divided by a to the power of n equals a to the power of m minus n. It's just a rearrangement of that in log form. And we get log base a of m minus log base a of n equals log base a of m divided by n. So if you subtract 2 logs with the same base, you divide the bits on the inside. It's very, very similar to the second log law. And doing another clever example of that, log base 4 of 96 minus log base 4 of 3 is log base 4 of 96 over 3, which equals log base 4 of 32. Does anyone know 4 to the power of what equals 32? 2.5. How'd you know that? We did it earlier? Yeah. Nice. We did do it earlier. Thank you for remembering. So up here earlier, we didn't do that exact question, but our second example here gave us log base a of what of 32 equals 2.5, and the answer was 4. So that is equal to 2.5. You could evaluate that. You could put it into exponential form and equate them. 4 is 2 squared. 32 is 2 to the power of 5. You could work it out pretty quickly. And log laws 4 and 5. So the first one, this log law 4, is actually, I'm just going to put a little star here. That one's massively important. It comes up a lot. You'll see it come up a lot. So it's log base a of m to the power of p is equal to p times log base a of m. So what we're saying is if there's a power inside that log, then you can bring that out the front. It actually would have helped us in solving the previous question. Would it have? No, maybe not, because the 32 is there. But possibly. So if there's a power, you can bring that as a multiplier at the front. And this log law 5, which is specifically noted in your textbook, so I've decided to write it down, is actually just a variation on log law 4. Because log law 5 is, from here, log base a of 1 over m is equal to log base a of m to the power of negative 1. That's one of our index laws. And then you bring that negative 1 out the front, and you just get negative 1 log base a of m. So it is actually just this law put into practice with a negative indice. So 5 is just an extension of 4, and again, the boys could check for me, but I don't believe 5 is on the formula sheet, but 4 will be. No, so 4 is, isn't it? Yeah, cool. Okay, so there's that's all of them. That's the log laws, by the way. They're listed in your textbook, they're on the OneNote, and you're going to get a chance to practice using them today. I'm going to do some more examples though. This first example will be one of the power examples. N log base A of 2 equals log base A of 64, and we're going to try and evaluate the value of N and A. I believe. We'll see what we can find. It's tempting here to divide through by log base A of 2, which would be a problem. Because if we divided through by log base A of 2, there's no division rule for logs. There's a subtraction rule for logs that leads to a division on the inside, but there's no division rule for logs, so we can't do that. But what we can do here is we can equate the 2 and the 64, and we can recognise that 64, what have I been doing up here? 64 is equal to 2 to the power of what? Any takers? 6, good. 2 to the power of 6. So get used to those numbers that pop up in the 2's, powers of 2, powers of 3, powers of 5, and then be able to get to them quickly. 64 is 2 to the power of 6, so I get n log base A of 2 equals log base A of 2 to the power of 6. Therefore, n log base A of 2 equals 6 log base A of 2. And now I can divide through by log base A of 2 because it's a common factor, leaving me with n equals 6. Can I find A? The answer to that question is, in this question, we can't find A. So we basically now get to a point where we have 6 log base A of 2 equals 6 log base A of 2, and A could be anything. As long as it's the same on both sides, it'll still work. A could be 1.5, it could be 10, it could be 100. So we can't actually solve for A, but we can solve for N. So you've got to be a little bit discerning on your understanding, so you don't take this. A question like this, you could easily muck around with for the next page trying to find A, and then probably end up doing a whole bunch of things that aren't mathematically correct in your hope to find A, and possibly come up with an A that isn't the only answer, etc. So just be careful of that and be aware of it. I've got a 3-part question there, and then I've got an example 7, but I might do that later. So example 6, simplify log base 3 of 27 plus 1, and then 10 to the power of that stuff there, and then log base 2 of x minus 4 plus 3 log base 2 of x. So I'm going to do some weird and wonderful stuff here, which will provide you a little bit more insight on some of the things we can do with logs. I've chosen these examples very specifically to do this. So first of all, A I have chosen very specifically because this is a pretty easy question if you do it one way, but if you do it a different way, it's just as easy, but it just brings up one little piece of information which might come in handy in algebraic situations. So log base 3 of 27 plus 1, hopefully you can see that log base 3 of 27 is fairly easy to figure out because this is log base 3 of 3 cubed. 27 is 3 cubed. And you might sit back now and go, okay, 3 to the power of what equals 3 cubed? Do that questioning process, and the answer is 3. I know there's a lot of 3's in there. You might also just bring the power out the front. 3 log base 3 of 3 plus 1. And hopefully you remember that log base A of A equals 1. That was log law number 1. So log base 3 of 3 equals 1. So we get 3 plus 1, and we get 4. So the answer to that is 4. Any questions on that one? If I could just go sideways a little bit and show you a slight alternate, which is probably slightly harder, but there's one thing I want to point out in this alternate, because you might get questions like that where the 27 is actually an x, and you've got to do other things. So, log base 3 of 27 plus 1, let's say we wanted to combine this into one log. This is a bit where you might have to backwards design a bit and use log law number 1 to recognise that 1 can be written as log base 3 of 3. So we've got that rule, log base A of A equals 1. I've reversed that rule and I've written this as log base 3 of 3. I could have written this as log base 7 of 7, or log base 15 of 15, or log base 100 of 100. Don't use negatives. Don't go into the negatives. I will talk about why that is when we get to the functions. But for any positive integer, I could have done that. But I've chosen log base 3 of 3 because I've got a base 3 in the first one. So now I've got equivalent bases, which means I can combine them together by writing log base 3 of 27 times 3, which equals log base 3 of 81. And then that's log base 3 of 3 to the power 4, which is just equal to 4. So I get the same answer. The point I wanted to make here was this transformation. If this wasn't a purely numerical question and I had an x somewhere, or even if, say, the base was x, I might need to do this transformation here to get it into a single log. And then that might be my answer. So just be aware, sometimes, particularly with algebraic questions, recognising that 1 can be written as log base x of x is very helpful. So just keep an eye on that. That's question A. Question B, 10 to the power of log base 10 of 2 plus log base 10 of 3. Just going to scoot this down a bit. This is going to also rely on something that's just a little bit clever, and it comes from your question earlier, Baxter, and that is that logs and exponentials are opposite. They're inverse relationships. So they invert each other. So what I'm going to write here is kind of a general rule of that idea, which is that x to the power of log base x of y is just equal to y. So if I've got a log in a power, they're the inverse of each other. They cancel each other out. Just like some other inverses that you know. For example, the square root of x squared will just equal x, because the square root is the opposite to squaring. Or x plus 7 minus 7 just equals x, because adding a number and then subtracting it are opposite functions. So taking a log and raising to the power of the same base is an opposite function. And you can explore and play with that. If you look at it numerically, you'll see it happen in place. But for this question, I can't do anything like that yet. Even though I've got 10 to the power of log base 10, I've got 2 terms in my power. So the first thing I have to do is combine those 2 terms. Log base 10 of 2 times 3. Because when I add 2 logs and I've got the same base, I can just multiply the inside bits. 10 to the power of log base 10 of 6. And now, and try this if you want on your calculator. Evaluate log base 10 of 6. It will be something like 0.7 or whatever. And then do 10 to the power of 0.7. Or think about it like this. If you ignore that, this log is saying 10 to the power of what equals 6. If you evaluate what that special number is, and then put that number as 10 to the power of that number, the answer will be 6, because that's where we originally got that number from. So the log and the 10 will cancel out, and it will leave us with 6. And again, I saw you reach for a calculator, Harry. Did you get an answer for that log base 10 of 6? Yeah. No? Yeah. Yes. hold on a second. I'm going to do log 10. So, did you get 0.78? So we get log base 10 of 6 equals 0.78, and then 10 to the power of 0.78 equals 6, and that makes sense because that's where we got the 0.78 from. So they cancel each other out. I'm saying that makes your life a bit easier, but you can do it the other way. If it's algebraic, it's going to be an important feature. We will talk about it a bit more. So I've chosen these examples to pull out a couple of special things. The last example, log base 2 of x minus 4 plus 3 log base 2 of x. And we just want to simplify this. 3 log base 2 of x. So I can add 2 log base 2's together, but the second one has a 3 out the front at the moment, so I can't add it together yet. It might be tempting to add it together and put a 4 out the front, but you can't do that. You can only add logs when they're singular. So I've got log base 2 of x minus 4 plus log base 2 of x cubed. That's the reverse of index law of log law number 4. So I've just put that number out the front in as a power. Now that I put it in as a power, I've got log base 2 x cubed times x minus 4. I multiply the things inside the logs when I add them together. I get to there. I don't want to scare anybody, but we could easily give you a question where we say that equals 10, that equals 10, 2 to the power of 10 equals this. Now you've got a quartic to solve. So, believe it or not, and I'm pretty sure it'll happen in this exercise, quadratics will almost certainly come back again to haunt you. And they will come back again next term and just continually come back for the rest of the next year and a half. So I apologise about that in advance. But that's the simplification there. That's as far as we can go because it's not an equation. And I'm going to leave it there and ask you to just carry on now with the work from exercise 13F. I will leave example 7 up so you can have a look at that if you want to.